audible.
Okay. So, good afternoon, everyone. Once again, I welcome you all participants for this short-term course that is based on applications of machine learning techniques in sustainable technologies 2024. Now, we would like to resume the next session with Professor Indrajit Sarkar. It is my pleasure to introduce Professor Indrajit Sarkar from National Institute of Technology, Rourkela. Dr. Indrajit Sarkar received PhD in Electrical Engineering from Indian Institute of Technology, Bombay in 2018. He has nearly 7 years of industrial experience working in the areas of power electronics converters for renewable energy and HVDC. His areas of research interest are EV battery charging system, renewable energy integration, solar EV charging, DC-DC converter, multi-level converters, and induction motor. He completed his BE degree in electrical engineering and ME degree in power electronics specialization from the IIEST Sipur, Howrah in 2005 and 2012 respectively. From August 2005 to June 2010, he has served as graduate engineer in ITES for energy and utility customers, Tata Consultancy Services Limited, Kolkata. From 2012 to 2017, he was a full-time research scholar with the Department of Electrical Engineering, IIT Bombay. From 2017 to 2019, he has served as R&D engineer of HVDC grid system with ABB Global Industries Service Limited in India. In July 2019, he joined Department of Electrical Engineering of MNIT Allahabad as assistant professor. Dr. Indrajit Sarkar joined the Department of Electrical Engineering of NIT Rourkela on March 2020, where he is currently serving as assistant professor. So now I request Professor Indrajit Sarkar to proceed further.
Thank you, Ananya, for the introduction. So now we'll start. Let me share my screen first. Can you see my screen?
Yes, sir.
The PPT is visible now?
Yes, visible.
Yes, sir.
Okay. So good afternoon and welcome you all for this session. So today I'm going to discuss about this EV charging and how machine learning will able to help the EV charging scenario in order to improve the grid stability. So this is the main topic that I'm going to discuss in next 1.5 hours or 2 hours. So now, before I proceed to this, let me talk about the state of art that we have with the EV industry and all. So currently, there is a trend towards EV. There is a trend towards electric vehicle. Okay. So reason is what? What is the reason for going into EV? Can anybody just tell me what is the reason we are moving towards EV? Any idea why there is a craze to go towards EV?
Sustainability.
Sustainability. From where it will come? That's fine. That's absolutely correct. Economic. Okay.
Now to reduce the
Okay,
CO2
economic.
emissions.
Acha, to reduce emissions.
Pollution would be less.
Pollution would be less. Okay. Then any other reason? Let's say you want to buy an EV or e-rickshaw, sorry, e-bike, or let's say EV, a car, electric car. What would be the motivation to buy that car?
Less dependency on
To
fossil fuel.
reduce carbon and less charge for fuel.
Okay. Okay.
Lesser running
So
cost.
That is a reason increase in fossil fuel prices.
increase. So cost is the, when you are as a customer, so we'll think from cost point of view, right? That my running cost would be less. That is the reason behind that you are going to pay maybe a 5 lakh car which you can buy, which is IC engine based, fuel based vehicle. You're going to buy the same kind of car at maybe 15 lakhs or so, since the cost reduction is there. That is the main motivation from customer point of view, right? Now EV, the EV manufacturers are making EV. The reason for EV to be popular is, the first answer was sustainability. Okay, so sustainability is in the sense like we are trying to reduce the dependency on fossil fuel. Okay, dependency on fossil fuel. Now, when we are reducing dependency on fossil fuel, then what would be the source of energy that we are going to use for driving those vehicles? So the so source is renewable energy. So solar is one of the most popular renewable energy that we are having currently, and also in future, near future. The hydrogen is the future. Now, few answers were the emission reduction. Let me tell you why I am discussing all these things. You will try to, you will get to understand. When we are using an EV and we are consuming power from the utility grid, then our purpose is not served. Why our purpose is not served is, when you are charging, let's say in India, where renewable energy integration is yet to, means it's not that substantial. It is mainly fossil fuel based, like coal based thermal power plants, from where we are getting power. Now our grid is based on those power plants. Now there we are burning coal. Now when we are charging an EV from those power plant emissions are increasing. So if we are not utilizing the power from renewables, the success of EV is not there. So if you are saying we are reducing carbon emission, carbon footprint, we are reducing the pollution and all, that is not successful until and unless you are completely, the cycle is complete with no emission. You are charging EV from coal-based power plant, then you are not. You are actually making your city clean, but actually you are making out of the city dirty. Okay, so why we are talking about sustainability? Because if we can utilize the renewable energy sources to charge an EV, then definitely there is a success for EV. Now, the most hurdle for the success of EV is the source, which is a battery. Okay. Now, battery, there are researchers are going on the battery. But thing is, when you are driving, let's say a petrol bike, and when you are driving an EV, there is a difference between these two. Is when you are driving a bike which run on, let's say, petrol, so immediately go to a petrol fuel station, and then you refuel it immediately, maybe 10 minutes or so, because there are lines. Okay, otherwise if it is you are the first customer, then it will take merely 2 to 3 minutes. When it comes to EV, then EV battery takes time to charge, maybe overnight. Okay, and also there are, from Indian scenario perspective, I am telling you that there are n number of e-rickshaws are coming up. I went to different cities where I have seen e-rickshaws are very much popular, and those e-rickshaw is mainly used for business purpose. So for the whole day they are running the e-rickshaws, and then they are going home and charging it for whole night. So 10 to, let's say, 8 to 10 hours they are charging. So charging an EV battery is a problem. Problem in the sense, it's a problem. Solutions are there, definitely solutions are there, and that solution is creating further problem to our grid. So those things we'll discuss one by one. Now I talked about sustainability that I discussed. I mentioned about sustainable DC fast charging. So I mentioned about why sustainability I'm talking about, and DC fast charging why I'm talking about. As I told you, that it takes 8 to 10 hours. So an e-rickshaw person, let's say he started his business early in the morning, maybe 6:30 or 7, and then he immediately, means after maybe by 12 p.m. or so, his charge is exhausted. Okay, now he cannot use his e-rickshaw for the business purpose, because he has to he has to charge the e-rickshaw battery for again 8 to 10 hours. Then there is a problem. There is a problem. How to mitigate it? Then what you do is you do DC fast charging. What is DC fast charging? So what you do is you charge the battery. It's like a tank. Let's say you have a water tank, and then the water tank, you can fill the water at slow rate, or you can fill the water at very high rate. When it is very high rate water is coming into the tank, then tank will be filled very fast. And when it is water flow rate to the tank is low, then it will take much time to fill the water. Now what is the meaning of DC fast charging is, you are charging the battery at very high current. You're charging the battery at very high current, so quickly your battery will get charged. Okay, so this is what the DC fast charging is. Now when you are having this kind of DC fast charging, it loads our utility grid heavily. So how machine learning is going to help us in order to reduce these things, that we'll discuss here. Now, so here first I will discuss about whatever I told, that how to charge an EV and what is the DC fast charging. Then I will talk about multi-port converter. What is multi-port converter and how it will give rise to the sustainability, that I will discuss. And then grid connected EV charging. And then I will move into electric vehicle charging management using machine learning. So here I have one example. Okay, this is a car which is Nissan Leaf. It is very popular in US. So in Nissan Leaf, what we have, you can see here. So you can see here. So it is having a battery of 39 kilowatt hour. It is having a big battery. Okay, and its voltage level is 351, which is for this condition it is not that relevant. But what we are interested on, that this is the charging time. This is the charging time. Let's say you are using that car, and the battery has gone down to some minimum level, and you want to charge it. So at home you have to charge that. This is the charging power level, 3.6 kilowatt. Okay, this is the at home, you cannot go beyond this. Okay, so at this charging level, at this charging power level, you can charge this 3.9 kilowatt hour battery to full. It will take around 13 hours. So it will take huge time. Okay, if you have time, fine. If you don't have time, then there is another option available, which is DC fast charging. DC fast charging. Now the DC fast charging, you can see here, it is 3.6 kilowatt. It is 46 kilowatt, and it is DC 46 kilowatt. Now at this point, let me tell you, if we are asking for 36 kilowatt power, 36 kilowatt power from the grid, this power is taken from the grid, and that grid is from distribution grid. What is distribution grid? The grid that is available. So when you go to your locality, when you're living in your locality, and you will see there are transformers and lines are there. Okay, so from that line it is coming to your home, and that voltage is 230 volt. That is phase voltage, and the line voltage there is 400 volt. So this system is called distribution system. So 36 kilowatt power we are consuming. This is one charging station. One charging station of 36 kilowatt that is used to charge an EV battery. One home is consuming, a typical example, one home can consume a power of 2.5 kilowatt. So there are maybe, so how many homes? 20 homes, 20 homes. Okay, so one charging station is going to consume 20 home power in order to charge an EV battery. So it's an enormous load that you are going to put on the utility for a short duration, because how much time it is going to take? only 43 minutes. In 43 minutes, it will charge your EV battery. Okay, so for that period, the amount of loading that is going to happen on the grid is huge. So immediately it will feel like immediately you have loaded. So let's say in your locality you had 20 homes, and then when you started charging DC fast charging of your EV battery at 46 kilowatt, then immediately the grid will feel that another 20 houses immediately put into loading on that same grid. So it's a grid, you cannot play like that. Okay, it's a problem for the grid. Grid may go into instability, means the grid stability may go. Okay, so we need to mitigate it. That is the problem, and we need to mitigate. How we can mitigate that, we'll see. So now this one example I have taken, that when you are charging at DC fast charging that we do, then its charging current is huge, around 100 ampere. Whereas it is when you are charging at home, it is only 9 ampere, around 9 ampere. So 100 ampere, 9 ampere to 100 ampere. That is what DC fast charging. That's fast charging that we do for Nissan Leaf, which is a standard car in EV car in US. Then let's say Arthur bike is available in India also. So here also we can see that here we can see that it's a bike. So its battery is a small battery, so 2.4 kilowatt hour. So there are 48 volts. So 4 batteries are in series. So total is 48 volt. And here we have 2 chargers. One is called Arthur dot, another one is Arthur grid. So Arthur dot is available for 720 watt AC. So this is much lower level. Okay, much lower level. But DC fast charging option is also available for Arthur bike, which is 3.3 kilowatt DC, which will charge your bike in 50 minutes. You no need to wait for 5 hours, 4 hours, 30 minutes. Within 1 hour, it can charge your battery. Now, somebody can ask me that, sir, why we cannot have, instead of 3.3 kilowatt, why cannot have 10 kilowatt or so? 10 kilowatt, let's say, charge at 10 kilowatt. So this time will reduce to maybe 15 minutes or 20 minutes. The problem is battery. There is a capability that battery can take. The capability of current the battery can take. So here the battery can take up to, let's say, 65 to 70 ampere current it can take. You cannot charge more than this, then it's very, very harmful for a battery. And also this also you cannot charge for a long period. Okay, this is not acceptable. You are charging a battery for a very prolonged period is also not acceptable. That deteriorates the battery lifetime. Then we have eRikshaw. I have taken this into consideration because eRikshaws are increasing, number of eRikshaws are increasing, and the loading of eRikshaw on the grid is also increasing, and the typical hour when they are charging is night time. So during night time, load on the grid is increasing, or maybe from the evening itself they will start charging their vehicle, and it's increasing. Now here also we have this solutions are available. So Vidyut Vahan Viva charger is available for Redsol Energy Solutions. It's a grid connected rapid charger, they say, and it takes 90% less time. 90%, let's say if it is 90%. So maybe in 1 or 1.5 hours they will charge the eRikshaw battery. Okay. There are 15 kilowatt Bharat charger for DC fast charging is also available, and there are other options are also available, but these are not popular till date. Okay, not popular in the sense you cannot see very regularly people are using this. You will see that eRikshaw players are using a slow charger that they use. And also another problem with eRikshaw players is there is no charging station available. Charging station, if charging stations are a number of charging stations are available, then it's beneficial for them. Beneficial for them. And also this, if it is if it is a charging station, the charging station has to be fast charging station. So if you are installing charging station, that charging station has to be fast. so that they will come and within half an hour or 40 minutes they will charge their e-rickshaw and they will go. So that kind of infrastructure we need to build for them. So since we are talking about sustainable EV charging, so that the option that we have is we need to use solar power to charge your EV battery. When you have solar power to charge your EV battery, there is a problem. There is a problem in the sense solar is not equally solar power. When you have a panel, let's say you have a panel, and if you feel that the panel will give you constant power throughout the day, this is not going to happen. That during the complete day, let's say from morning 6:30 to evening 5:30, the power available from your solar panel is not equal. Okay, so in order to mitigate this issue that power is not equal, what we have to have is, let's say we have a battery storage system, and then you have e-rickshaw battery. This is the solution configuration for sustainable e-rickshaw battery charger, where you have solar PV, then you have battery energy storage system, and then the e-rickshaw will come, charge, and will go. So this kind of configuration you can install anywhere in the city, and then e-rickshaw will come. It is not connected to the grid, so it is not taking power from the grid, and then e-rickshaw will come and go, charge and go. But the problem is it is not DC fast charging. This is not fast charging. Okay. Now, why we need this battery energy storage system is something like, let's say you have municipal water supply coming to your home, and it is coming for, let's say, 1 hour per day. So morning 1 hour and evening 1 hour. So that means if you do average, so you don't have power water supply available throughout the day. So what you do, you install a tank, water tank. You fill the water tank and then utilize that water throughout the day, and when water is available, you fill it. Similarly, here also the battery energy storage system will act as a storage tank. It will store when there is a, let's say, e-rickshaw is not there to charge. So what you do is, from solar PV, whatever power is generated, it is going to store in this battery. And when it is there, then both will give power to charge it. Something like this will work. And there are different configurations where you have multiple converters, and then you have e-rickshaw battery. And there are configurations called multi-port converter, where you integrate all the converters together as a product. Now, one sustainable solution looks like something like this, which is isolated thing. So here we have solar PV, then we have battery energy storage system, and here is the electric vehicle. So say similar configuration, but topology is different. Sorry. Sound is coming. Okay. And now, so this I already explained that the battery energy storage is acting as a buffer for the energy. Now, we talked about DC fast charging. Okay, DC fast charging has harmful effect, though may not be that relevant here. But let me explain why it is not recommended, because any of you in near future is going to use an EV, and this information may help you whether you should go for DC fast charging or not. Okay. Now, slow charger, this I already explained that when it is slow charging, they are charging, e-rickshaw owner or EV, you are charging and then charging for, let's say, 10 to 12 hours, and then you are going out. And when your charge level is low, then you have to wait for another maybe 5 to 6 hours to charge it. So DC fast charging can quickly charge it, which I already told. And for e-rickshaw players, since there is no charging stations available, so what they have to do, they have to come back home, use their slow charger, charge, and then again go for the business. So this is also not recommended. So DC fast charging provides refueling experience similar. I can say similar. It is not that too very close to it, but it gives similar feeling that okay, my vehicle is the energy to my vehicle is refueling fast. Whether it is not comparable with this, but it has reduced to some extent. But the problem is DC fast charging of these deep discharge batteries shorten the battery lifetime. When you are doing high current, I gave example about the water tank. When you are filling water tank at slow rate and when you are filling water tank at high rate, the difference is the water level will go fast when you your water level is high, and there is no other harm other than you have to provide a high rate of water flow to the tank. But in case of battery is an electrochemical device. So when battery you are charging at very high current, you can see here the Nissan Leaf. You see here the amount of current that is going. Amount of current going to the battery is 130 ampere. So huge. It's supposed to go 9 ampere, but you are supplying 130 ampere. This is very high, and it is not regular recommend. We cannot recommend it on regular basis that you are going to do this. Okay. So why? Because so there is internal resistance of a battery, and when there is an internal resistance of the battery, I square R loss will occur. When I square R loss is there, the battery will heat up. You can see that you also all of you also have experienced this. Now this fast chargers, mobile fast chargers are available. When you have there is a dedicated charger for your mobile, and there is a fast charger like 2 ampere 3 ampere charger is there. You put on your mobile charge with that fast charger, your mobile will be heated up. It is actually not the mobile is heating, it is the battery that is heating. And it is because of that I square R loss. High current is going, there is a resistance of the battery, and I square R loss, and battery is heating. Heating of a battery is harmful for the battery life. So battery life, so if you do regular basis DC fast charging, then your battery life will reduce. Then it's a harmful for your battery. So it is suggested not to use on regular basis. And also it is not recommended for deep discharge batteries. Means you completely used, the batteries, charge of the battery is completely used. You don't do that. Why you don't do that? Because if you do that, then charging of the battery will take time, and for that time you are supplying a current of 130 ampere or so. It's not recommended. Let's say your battery has come down to certain level, let's say 60%, 70%, then you go for it DC fast charging, and it will not take much time, maybe half an hour to 40 minutes or so. You can bear, battery can bear that amount of time, maybe depending on battery chemistry and depending on what type of battery that you are using. But deep discharge battery, when you are going to charge with DC fast charging, it is not recommended. Your mobile phone is completely dead. Mobile phone battery is completely dead, and you put on it into the fast charger. That is harmful for your mobile battery. So DC fast charging recommended for smaller duration and to boost the battery SOC. Just to boost. Let's say 10%, 20%, 30% charging you are doing. It's fine that you do, but not full charging of deep discharge battery. That is not recommended. It is not suitable for your mobile battery. Now this here we explain where it is this charger, this EV charger is not connected to the grid. So it is autonomous. It is grid independent. You can install anywhere. But when you want to go for fast charging, the grid is the only option currently. Currently, grid is the only option. So there are different DC fast charging topologies are there. Topology is not relevant. The relevant thing is everywhere you can see that it is connected to the grid. So the power it is taking from the grid, and that to three-phase power, because single-phase power is not enough to supply that amount of DC fast charging amount of power to the for DC fast charging of the vehicle. So when you have renewables, even if when you have renewables, it is connected to the grid. So here we have shown two scenarios. Here we have power grid. We have power grid. Then we must have a transformer. Generally, we have a transformer. Then there is an AC bus, AC three-phase AC bus, and from three-phase AC bus you have different ports that is available, or it may be different charging stations. So at different charging station you are supplying power to charge the battery, charge the electric vehicle. Okay, and let's consider this as fast charging, which is already mentioned here. So fast charging. So even if there is renewable energy sources are available like wind, PV, and also energy storage, battery energy storage is there. So apart from that, grid is also there in order to supply power for DC fast charging. So here the bus is AC. Here the bus that we have is DC. So there are two different configurations where one is AC bus, common bus. Here DC is the common bus. But in both the conditions, it is connected to grid. Now there are standard chargers that are available in the market now. Okay, from different company. I'm interested on these two. One is Tesla supercharger. Tesla supercharger is for Tesla cars, where you can see here the amount of power it is taking, 135 kilowatt. So here, if you see in Nissan Leaf case, Nissan Leaf, it was only this was only 46 kilowatt, and that is for only one vehicle only. Maybe, sorry, this maybe this is this DC. Let me explain you one thing. There are chargers like level 1, level 2, and DC fast charging. Okay, so level 1 is a low power level chargers. Level 1 chargers are the chargers that we are using at home. These are low power level. Then we have level 2 chargers which can be used from single phase supply or 3-phase supply. And then we have DC fast charging, which are outdoor chargers. It's a large chargers outdoor, available at the outdoor. So these are outdoor charger, maybe a charging station. So there it is 46 kilowatt. Here Tesla supercharger. Here Tesla supercharger, it is 135 kilowatt. And then we have a charger from ABB, which is 350 kilowatt. So as I was telling you that 2.5 kilowatt a home can consume, and for a charging station it is taking 350 kilowatt or 135 kilowatt, something like that. So enormous amount of power that grid is going to take, since all these are grid connected. So enormous amount of power these are going to take from the grid for a shorter period. As I already explained that DC fast charging that you are not going to do for a longer period, you're going to do for a shorter duration. So for a shorter duration, grid is feeling like it's a huge amount of loading immediately has been done, and for a shorter period. It is like, so what will happen? Let me explain in another sense. Let's say there is a water tank, and there are 4 to 5 taps are there at the bottom of the tank, and then there is an inlet pipe from where water is coming to the tank. Now let's say one tap is open, the amount of power coming out of the tap and the amount of water coming into the tank is same, rate is same. Whatever water is coming inside the tank and whatever water coming out of the tank is same, then water level will remain the same. Now let's say intake water level we kept same, and then immediately we'll start all the taps. So what will happen? The water level will come down. Slowly water level will come down. Similar thing will happen in grid also. When there is no EV charged from, let's say, from Tesla supercharger. Okay, let's say no car is there to charge from this charging station. Now there are cars which are available in this charging station to charge, and that is for 27 minutes. That is for 27 minutes. For half an hour, the car is going to charge. So immediately when you have started charging, the grid voltage will come down. The grid voltage will come down, and if you don't take perfect measures, then this may lead to voltage fluctuation, or this may lead to grid failures as well. Not this case, or maybe when you have multiple charging stations and huge number of EVs started charging at the same time, those kind of catastrophe may happen. So here is a scenario. So grid connected EV charging. So here you can see that uncoordinated charging scheme means you have a charging station. The cars are coming, charging at the charging station, and this is connected to the grid and renewable energy sources. Similar to this. So cars are there, and then renewable energy is there, renewable energy, and just you bring the car and charge, and then you go. So this is called uncoordinated. There is no coordination between the grid, between the renewable energy, and between the cars and the car owners. It might happen that let's say there are 3 cars. It might happen that car 3 may wait for another 1 hour, and car 2 must go now. Why to charge them together? Just you wait, you keep this vehicle to wait and charge this one first. Charge car 2. So this kind of scheduling and scheduling should be there, and there is a management should be there between, and also there is a scheduling when to charge, and there should be a coordination between the load and the grid. So if you don't have any coordination, so it's a normal charging which is called uncoordinated charging scheme. Now what happens? Any product, for any product when it comes, let's say one example I can give you. When a product becomes a working prototype, or let's say a washing machine. Okay, when it's up, I didn't know about the history of the washing machine, but what I can understand is people thought like, let's invent a machine which can wash our clothes. So somehow they built a machine which was successful in washing their clothes. So they built semi-automatic washing machine, and it was working for some time. Then when it started working and people successful that yes, this machine is successful in washing the clothes, then why not to go one step ahead in the sense they invented fully automatic washing machine. Okay, so first aim is let the system work, let the system become successful, then we'll keep on improving, and then we'll improve the system. So here also now EVs are coming up. Now EVs are less, number of EVs are less, so DC fast charging stations are also less. So let's charge it. Why to bother about coordination and all? Now when the number of cars are increasing, then people thinking about, okay, then we have to save our grid. Why? Because you see here the load profile. Load profile means forget about this brown curve. So load profile is something like this, residential load. So residential
Sir,
load
PPT is
is
not visible.
Excuse me, sir. So slide not visible,
yes.
sir.
When it happened. Now or it's
minute or two back.
okay. So, wait. So visible now?
Yes, sir.
Yes, visible.
Okay. Okay. Thank you. So here, I was talking about uncoordinated charging scheme. So here, so there are 2 curves. Power system means who are generating the power in the transmission. There is a power system. So power system is divided into generation, transmission, and distribution. So generation people know, okay, this is going to be the load profile. This is going to be the load profile, and I have to generate like this. Transmission people know about, okay, this much amount I have to transmit. Distribution people also know that, okay, this is the load profile. But what about EV load? EV load means no. See, if you have 10 homes are going to consume this much amount of power, that or maybe plus minus. But it might happen that your EV is kept for quite a long time and you are not going to charge it. Or maybe immediately you went to somewhere and then you come back and you are charging. So EV charging of EV is random, and also EV is giving an extra load extra load to your load profile. So you see here the peak is more here. Why peak is more here? Because let's say people are using their car to go to the commute for the office and all, office, school, and etc. So they're coming back at night and then they put their car on charging. So during this time, you can see here from maybe 5 to this period, you can see there is a peak demand of EV charging. Peak demand of EV charging. Now you might ask that, sir, then will accordingly will let the these people, power system people know about this is the load profile. As I told you, this is random. This is random. Kind of load is not small load. It's a good amount of load. So the challenges that we are going to have now, we are coming to the problem. Okay, we understood what is there, what is the system. We understood till now. Then we are coming to the problem. What is the problem with the system? Now, in the system, what we have consumers. Can you hear me?
Sir.
Yes.
Yes, sir.
Yes, sir.
In our system, what we have the consumers, EV users that we have. Then we have the grid, okay, which is providing the energy for the EVs. Okay. Now the EVs are going to connect with the grid, and that connection is, and the consumption of power from the grid is random. Okay, and also this infrastructure is not in place till now. Okay, there are limited number of charging stations, and also the grid has not come to that smart grid. We are not working with smart grid. Smart grid yet to come, but our grid is conventional grid. It is old grid. Then what we can do in between, so that we can help grid and also help the users for this charging. I am not talking about the driving and all. I'm concerned about charging because it's a charging is not the petrol pump. It is charging from the grid. Okay. So what challenge that we are going to have? Voltage stability. As I mentioned about the water level example, that water level will go down. Here also, when you are going to put all the EVs together to charge, then the voltage level will come down. So here, what is the reason for this? So EV integration may have negative impact on the voltage stability. Okay. So here one thing is there. Before I'm going further on this, let me explain what is V2G. There is a concept called V2G or V2B, vehicle to building or vehicle to grid. It is like let's say it is like there is a water supply at your locality, and today the water supply is not there. Water supply is not there. Now your neighbor is running out of water. So what will you do? You are going to help him or her, and you will supply some amount of water to them, so that both of you can have water and you can sustain. So vehicle to grid mechanism is, let's say your vehicle is charging. Your vehicle is charging from the grid, so power is flowing from the grid to the vehicle. Now there is some problem in the grid. Okay, there is some problem in the grid, and that is because of some reason. So it might happen that electric the battery of your electric car might supply power to the grid to maintain the stability of the grid. It can supply some amount. As I told you the example, you are supplying water to your neighbor so that they can sustain. So here also you're supplying some amount of whatever small amount of energy you are supplying. If you have, let's say 20 homes, 30 homes, and out of 30 homes, let's say 10 homes are supplying power to the grid, it is helpful for that locality. So that is vehicle to grid. Sometimes this concept you might have heard, that you have a vehicle and the vehicle is charging, and let's say there is a power outage. Your vehicle will act as an inverter and your entire home will be Home will be running from by consuming energy from your car battery. That concept is there. It's old, not very old, but yes, it is there. So that is the same concept that I am talking about here. So voltage stability. So due to different load characteristics, different vehicles are having different kind of load characteristics, and also these EV, all the EVs if come together, then it's a problem. So implementation of vehicle to grid system that I already explained, that can help the voltage stability. Then comes your part, the machine learning part, optimization of EV charging schedule. So you can schedule, optimize the EV charging schedule using some algorithm, so that schedule becomes, the charging profile becomes distributed. Okay. Implementation of smart EV charging based on certain parameters. What you do is implement smart charging system, so that it takes care of like coordinated, like there will be a handshaking and there will be decision making based on the parameters that are available to you. And then implementation of accurate model also can help you the voltage stability. Then what is frequency stability? Okay. So when you, all of you know that when there is a grid, that grid is having two parameters. One is voltage, another one is frequency. So there are two chances of failure. One is voltage failure or maybe frequency failure. So voltage failure is called voltage stability, okay, instability, and frequency instability is when frequency goes in India, it is 50 hertz. So we keep the frequency between 49.5 to 50.5. So if it goes beyond that, then there is an instability. So if that is the case, so how it can be mitigated? So voltage deviation increases due to penetration level and charging rate. This frequency deviation, it should be frequency deviation. So implementation of V2G, as I already told you, and then use of multi-objective optimum charging control strategy. So you optimize the charging control strategy. That will see how we can do that. Then rotor angle stability is another stability criteria. And so coordination between EV load and wind farm. So power generation and EV load, as I told you, if you can make a coordination between them, yes, you can improve the profile significantly. So these are the stability classification. So when there is a power system which is charging the EVs, there are voltage stability, frequency stability, and rotor angle stability, and all that I already mentioned. Now comes to coordinated charging scheme. In coordinated charging scheme, you can see here what is this, that I will see first, that I will see later, but let's see this one. You can see here the difference. You can see this residential loads remain this blue, that is there, but on top of that EV charging was there in this blue color, brown color, which was having peak here. This peak shading we have to do. That this peak no need to take from the grid. If you have other sources, you meet it. Okay. If you don't have other sources, distribute it. So what they did is they distributed this load. The load remains the same, but they distributed. How this distribution has been done? It is by coordination between the load and the load and the generation. Okay, so you see here there's a coordination between every element that is available in this system, and there is a supervisory control that is available. So you have to supervise, and accordingly you have to take decision. So we have communication lines, so information and charging control. So all these things are available in that system, and accordingly decisions are taken. Okay, so what are the challenges when you going to employ this EV charging from the grid? The challenges are supply and demand imbalance. So you have to match. You are asking for more power. Okay, it is like, as I told you, that tank is having 5 taps and you are having 1 inlet. So when 5 taps are open and inlet remains the same, then what will happen? Water level will come down. So instead of that, if you 5 taps are open, means you increase the water inlet, then the level will be maintained. So demand and supply are maintained. So whatever supply is coming, the demand is also consuming. So if that you can maintain, yes, definitely your profile will be improved. Then you have to reduce the power loss. So significant quantity of real power is consumed from the grid. Huge amount of power we are consuming, and no system is lossless. Every system is having some loss, and when you are consuming more power, loss will occur more. Okay. And then component overheating means when there are transformers and other elements are there, when we are overloading a system, the heating will occur. So EVs are connected to a grid as is additional load to get charged. So uncoordinated EV charging increase the peak load, as I already shown. So implementation of off time to use time of use. So time of use you can, so there are now there are billings are implemented like, or tariffs are coming like, let's say they are trying to, when let's say a particular element is used for a long time, a particular time, a particular device, let's say washing machine, daytime people are using, almost every home is using it. So if you tell them, if you use your washing machine at other time and your tariff will be less, so you can distribute the load, something like that. So that is how is done here, tariff based, so that the EV load is distributed now. Implementation of appropriate charging management infrastructure. Okay, we can implement charging management infrastructure, so that that kind of coordinated management. So implementation of coordinated charging, and then an optimum combination of all three EV chargers. Let me explain this. What is level 1, level 2 and level 3, or level 3 or DC fast charging? What is this? Now, as I was giving example here, okay, so this vehicle 2 has to go first and vehicle 3 has to go last. Okay, he has time. So what you do, if you do go for DC fast charging for both the vehicle, what will happen? It will overload the system. Instead of that, what you do is you do fast charging for this vehicle, because it has to go now, and do slow charging for this vehicle 3. So the amount of power required in previous case, when it was no decisions were taken based on anything, okay, vehicle is there, you have to charge, so put it on DC fast charging. So huge amount of power that you are loading the grid. Instead of that, what you can do is you can distribute, like you do this at fast charging, you do this at slow charging. Then what will happen? The charging load, the charging load on the system will reduce. So that kind of thing we can do, and we'll see. So vehicle 2 you are charging at level 1 or level 2. So amount of power required is less, and level 3 you do at fast charging, and adaptation of fast charging concept. So now we come into this electric vehicle charging. Okay, before going to machine learning, just till now, whatever about the system description and the problem with the system, if you have anyone have any queries on this, let me explain about the system and the problem that we have with the system. If anyone is having, because that is separate part, this is separate part. That is more about the system, that you get to know for what system we are going to do what. Okay, what is the problem, and then you have to mitigate with, if we can see whether machine learning can help us here on. So if you have any question on that part, then I can explain. Any question that I can address?
Hello, good afternoon, sir. Hello.
Can you hear me?
Yeah, yes, sir. I can hear. Sir,
Okay.
I want to ask that we discussed about the grid system and taking power from grid and charging the electric vehicles. So at each part, we are trying to convert AC into DC. So here we are talking about the converter at each step before charging our electric vehicle. So, sir, the concept and the design part related to converter, that itself is a complete different topic in terms of power electronic. And now when we are trying to talk and learn about fast charging of electric vehicle using I mean DC charging. So what about this converter aspect, and how to differentiate between this and the entire process that you discussed, sir?
Okay.
Yeah, in
Okay.
terms of
So
research, I mean to say in terms of research, if I want to make an objective as to plan and design a converter, and then go for the fast charging of DC vehicle, and finally that should be optimized using machine learning. So that converter part is playing an important role. So how to correlate these points? If you can tell some points in this, sir.
okay. Now see, your point is valid. Okay, your point is valid in the sense. Uh, let's say you have a bucket of water at your home. Okay, so when you take a mug of water from that bucket, the level of water will go down. Now if the size of the bucket increases, then if you take one mug of water out of it, then the level will reduce. Small amount of level will reduce, water level will go down. Now let's say you have a water tank of 1,000-liter water. So if you take one mug of water, nothing will happen. Let's say you went to a sea beach and you're taking one mug of water, nothing will happen. So from your question point of view, since I discussed till now, the EV charging are from this DC fast chargings are everything from the distribution grid. It's from the distribution grid. Okay, all we have considered here whatever grid we have considered, all are distribution grid. Distribution grid is 400-volt distribution grid. Okay, so when you are taking from distribution grid and that amount of power you are taking from distribution grid, there is a chance of voltage frequency, etc., fluctuations, variations are there. Now, instead of that, what people have done this is people going into taking this power, DC fast charging power, from higher level grid, medium voltage grid. Okay, so higher level grid, when you are taking that much amount of power, the fluctuations, variations are less. So when you are going into that, then here you can see that for DC fast charging, you have multiple converters in parallel. Multiple converters, power electronic, mainly power electronic converters are in parallel. When you are going to medium voltage level, then your converter configuration design is completely different. We go for multi-level converter, we go for other converters in connected in series and parallel. Those series parallel converters are not that common, because when something, let's say there is a work and two-person is working, definitely one will work more, another one will work less. That will definitely will be there. You cannot have equal sharing of work between them. So here also, when you connect the converters in parallel, so the converter power sharing has to be there. That's a difficult task. So instead of that, we put one converter, and that converter is connected to the medium voltage grid, and research is going on that part, so that we can take this 150 kilowatt, 350 kilowatt amount of power from medium voltage grid. Not only one station, there are multiple. If you go and see the map, Google map, if you go and see Tesla supercharger website, you'll see multiple charging stations are available. So if you have multiple charging stations, so definitely huge 150 into, let's say, 20 charging stations, so a huge amount of power you have to take. So those power will come from that 400-volt grid, then it's a problem. So what people are thinking of, going to higher power, higher voltage level grid, and the converter also they are going to design accordingly. That is the thing.
Okay, sir. Okay, thank you.
Anyone else? Okay, so let's move on into the machine learning, how machine learning is going to help us. So as I explained here, that what are the problems that we have, that let's recall this. So charging large numbers. So till now, since the number of EVs are limited, okay, we are not having huge number of EVs currently. Even if in India, if we talk about India, so electric cars are coming up. Electric bikes are. I personally feel like I was feeling like it will come, but it has already arrived. The EV arena is already arrived, and there are multiple EVs I can see in the Rourkela city and can see in the campus itself, and also this EVs are coming up. This Tata Nexon EV is very common these days. I can see, and then other companies, other brand companies like Mahindra and all also are selling EVs. So it has already come. So till now, since the scenario was not there, now since number of EVs are increasing, this scenario is not very far. This scenario is not very far. This scenario is not very far. We are not, since it is yet not arrived. So now we cannot see people are talking about this. When it will arrive, there will be multiple occasions people are thinking to how to mitigate this. So if we have multiple EVs, cause substantial stress on distribution grid. So distribution grid is 400-volt grid. So load curve moves upward, increase the load on the transformer. So load curve moves upward, as I have shown that the EV is going to add a delta amount of power that has to be consumed from the grid. But that delta amount is not insignificant; it's a significant amount of power. And since there is a transformer installed at your locality maybe 20 years back, it is already overloaded. Now EVs are coming up. You are not going to the fuel stations. You're charging your EVs. So you're overloading those transformers further. So there is a load on the transformer is increasing. So intelligent and effective management is needed. Intelligent and effective management is needed. So if it is from home you are charging, okay, from home it is maybe in 100 home, maybe 20 home or 30 homes are having EVs. Okay, so may not be of that concern, and you are consuming less power. But when you are going out and you are charging from a charging station, and that too it is DC fast charging, then if you have multiple DC fast charging station, then the system has to take a decision. Okay, you as an user don't go to this charging station 1, go to charging station 2, where your cost will be less, charging cost will be less, charging will be fast, and also by doing this is your benefit. Okay, so you will get fast charging and your cost will be less. From grid point of view, the grid is distributed, the grid loading getting distributed, and from charging stations point of view, every charging station are getting the users. So intelligent and effective management is needed to allow distribution grid to deliver power with higher efficiency and reliability. So reliability is a very big term. When you make a product, okay, in every day paper is coming and there are researchers are proposing different methods and different products. But when you go to an industry, it first checks the cost and the reliability of that solution that you are providing. If your system, it's a low price, I'm happy. Low price, user is happy. But you come home, use it, and immediately next day that is stopped working. Now you are going to report to the shop owner. You are going to report your friends. You are going to report this to Facebook, Twitter, everywhere, that this is the quality of the product. So if reliability is not there, then it's a huge problem. So reliability of power system, you are supplying power to every home. So reliability has to be intact. So requirements of distribution grid and negative effect of charging on the grid needs to be considered. Okay, so what grid wants? Okay, grid wants what? The voltage fluctuation should be within this limit. Frequency fluctuation should be within this limit. And then when you go for uncoordinated charging on the distribution grid, it might happen that it is crossing those limits. It is not within the limit, you are crossing those limits. Now, you may immediately think that then when there is a need for power, I will supply from the renewable sources. Let's say you need 100 watt of power and grid is having only 50 watt. So the rest 50 watt I will supply from the renewable energy. Yes, definitely you can do that. Installation of renewable energy is free, definitely. But installation of renewable energy solution takes time. it's a cost, the initial cost is more. So immediately if you think that okay, there is a problem, you immediately install a solar charging station there. It is not feasible. You need space, you need infrastructure for that. So if you install, yes, it can do this to some extent. As I told you that vehicle to V2G technology can mitigate the issue. Okay, it can supply. Definitely, it is very from theory point of view. If you think yes, what is the harm? I was charging from the grid, and now you are supplying to the grid. Definitely, grid will give incentive to you. When you are consuming, you have to pay. When you are delivering power to the grid from your electric vehicle, grid is going to give you incentive, but even then it is not recommended, or even then it's, I should not say not recommended, user will not allow it to do. The reason is explained here. Okay, so V2G technology can also mitigate the issue and helps improving efficiency and reliability, stability and reliability of the grid. Regulates power, load balancing, current harmonic filtering, all those things can be done. This is out of this scope maybe. Okay, scope of this machine learning and all, because this harmonic filtering and all, current harmonic filtering and all is part of power electronic converter and its control. Now see what happens. Vehicle to grid technology. Your vehicle is a small vehicle with respect to grid, and you are giving power to the grid. So grid will consume the entire power of your battery. So there will be discharging of your battery. Discharging of a battery is not recommended. It's not good for your battery, EV battery. So when you go for vehicle to grid technology, then it's a problem for your EV battery, and then battery degradation and battery lifetime will reduce. So customer satisfaction is not there. So customer may not go for vehicle to grid technology. So you left with intelligent charging strategies. You left with intelligent charging strategies and coordinated charging. So whatever infrastructure that you have, use that. Within that, you do some charging algorithm, or you do some coordinated charging and all. So researchers are looking for EVs to be charged smartly. Smartly means it is not like you went to a station and then you charge smartly. It is not like that. Vehicle is there, options are there. One vehicle user is there, and there are different options, charging options are available. One charging station you have level 1, level 2, level 3 charging option. Your algorithm has to decide for this particular vehicle which level of charging that I am going to employ. So if you are going to build an algorithm based on that, that output of that algorithm should give, okay, you go to this charging station and you go for this level of charging. Based on certain input you have to give, and based on that it will take that decision, and that decision should be available to the user. So EV to be charged smartly, efficiently, cheaply and cleanly. Cheaply means from user point of view, it is in their it's cost beneficial for them. And cleanly means as I shown you that we have renewable energy sources, then you have grid. Let's say your supervisor control, take the decision, if sufficient amount of power renewable energy is available, let it use. Why to take from the grid? It is not like uncoordinated control. Okay, in uncoordinated control, both are supplying. There is no coordination. Now, in coordinated control, the supervisory control or your algorithm is going to take a decision from which charging, which power source that you are going to take. If it is renewable energy sufficiently available, take it. And constraint is you have same old grid, and you have to protect it. You have to give some offer to that grid that okay, my algorithm is going to distribute the charging power from this location. So distribution grid means you have different locations, charging stations are available at different locations. There you can distribute the EVs to every charging locations. So at the same time, at the background, these things are going on, but you as an user, you should not know that what is going on. The only thing that you are going to get on your mobile or some app, that okay, you go to this charging station and there you will get less amount of charging cost. Your charging cost will be less. So the user will get to know that okay, I have to go to that charging station. He or she doesn't know what is going behind. Okay, but that system is there which is distributing the load. So grid is there, charging stations are available. Only your guiding or routing your users to different charging locations. That management you have to do. So researchers at US Department of Argonne National University and student at the University of Chicago collaborating to train an algorithm. Okay, these details are available here. So train an algorithm to schedule and manage the charging of a diverse set of EVs. Okay, there are n number of EVs are available, not n, a certain number of EVs are available, and they are training an algorithm to schedule their charging pattern. So train the model. What is the constraint? Constraint is scheduled charging time within which you have to charge. Scheduled charging time means there are, let's say, 5 cars are there. Now you have to schedule them. So the user will give input that okay, this is by this time I will go out. Yeah, and my charging level is this. Charging level you get to know from the EV. So my charging level is this. I have to go now, or I have to go by this time. And also there is a certain limit to the peak demand. Yeah, grid has said that I cannot supply more than this, and there is certain amount of renewable energy that is available to you. So these are the constraints that to train the model. These are the constraint input that you have. Okay, so multiple EVs charging at the same time will create peak load, which is already mentioned. The reinforcement learning in the algorithm will work on certain feedbacks. Time, duration, as I told, that time, duration, how much time that you have, and how much charge that is available in the car, and the charging has to be done after certain peak threshold. Now there is a peak, you cannot charge now. The peak means there is a load peak on the grid, you cannot charge this time. Okay, you wait for some time and after that you charge. So based on this data, scheduling algorithm you have to make which becomes more efficient and intelligent. So there are constraints, there are reinforcements, you're reinforcing your algorithm, and accordingly you are taking decision to have efficient and intelligent and optimal smart charging schedule that you are making. So that group of people have made a mobile app, eRikshaw, allows network charging stations. So there are network charging stations are available. So an user can reserve station and participate in smart charging. So they can reserve, okay, this time I will go to this charging station and I will charge this my vehicle. My charge will be this much amount anticipated. This much amount of charge will be left in my car, and then I will charge for this amount of time. So accordingly, these details you give, and you can book the charging and you can go and charge. So hassle-free from user point of view, hassle-free from the charging station point of view, and also it is helpful from grid point of view. So it collects that mobile data, that mobile app collects data on charging behavior, how a person is charging, that it can record, and use this data to train future AI models to aid in smart charging management and vehicle grid integration. When to integrate that vehicle with the grid, or whether you, at what time you should. So those decisions can be taken. So electric vehicle charging management using machine learning. So this I already told multiple times that high number of EVs, if it is there, it has to be addressed. So increase load, power loss, voltage fluctuation. So charge management and charge scheduling of EVs are required, and that has to be done using machine learning. So that to so route the EVs to the charging station to minimize voltage fluctuation, power loss, the load variations. Okay, load variation was there, so peak load shading can be done. Okay, that time is peak is coming, so it is recommended that time you don't go to any EV charging station, you wait for some time, or you go to this location and you can do the charging. So at the same time, it will take whether it should be fast charging, conventional charging or fast charging, and also whether the user will participate in vehicle to grid charging scenario or not. That also can be incorporated. So machine learning to optimization the charging at suitable charging station and suitable charging speed. Okay, as I told you, at what whether so which charging station he or she will go, and at what charging speed he or she is going to charge his vehicle. Optimize the distribution network operation. It can optimize them to minimize load variations, minimize charging cost, as I already told. So depending on time and load uses of different buses in the network. So every bus, so let's say in this algorithm that you are going to make, we'll consider a power system network where you have different buses, and every bus should have a charging station, and those buses we will consider, because we are considering only the locations where charging stations are available, and then it will enroute the EVs to available charging station and find most appropriate charging speed to optimize the performance of the distribution grid. It is not going to give so you are going to make that algorithm that I'm not going to give all the EVs DC fast charging. Since you have time, you wait. Now there are, you must be knowing, these are the I haven't gone through each and every this machine learning algorithm. There are different machine learning algorithm. Now it might happen that study could be, there are also available studies are there. You using this technique, you check which technique is giving the best result. That can be done. Also similar kind of studies are there also. So you can check which machine learning algorithm is going to give better performance in terms of which parameter. Okay, so that can be done. Okay, and that can be used. So it might happen that for this purpose, this particular purpose, this machine the parameter optimization, this particular machine learning algorithm that I'm going to use, that study can be done. So to use a machine learning, what you need is you need an appropriate data set, and that has to be a good amount of data has to be there. So now there are datas are available. There are data hubs are also available from where you can get the data, and you can use those data to train your model. So multi-level machine learning algorithm functions automatically. So you have to, with exception of tuning parameters based on heuristic and trial and error. Okay, so formulation of complex equations and optimizations are not required. So transfer learning can be utilized for transferring machine learning models for different applications. You can use it for different applications, and also within application for different parameters also you can utilize different algorithm as well. So parameters that you are going to use here is there are different parameters. Let's say some input should be there and some output should be there. So machine learning model parameters, this could be the, so till here so till here you have to give input. What are the inputs that you are going to give? Month, day, hour, minute. This is standard time for me. Okay, now bus power load. So you have to know how much power is available at what bus. From that, the decision can be taken whether you have to give in every bus that power, the power that you are taking for that particular bus, that every bus should equip with one EV charging station. If that is the case, then you get to know whether the EV charging station connected to available at that bus, whether you can send an EV for charging or not. That decision can be taken. So that power you need to know. And also, as I told you, that peak load shedding should be there. So that total power available, how much power available, that also you need to know. Based on that, the decision you are going to take. What decision that you are going to take is the values are the number of buses with charging stations. So which charging station you should go. Okay, which charging stations are available for charging and which charging station is suitable for your EV charging. And then charging speed also, I will show you how to take that. So charging speed, so if the vehicle is going there and at what charging speed that you have to charge your vehicle, that also will give your, you should come, it should be the output of your algorithm. So one algorithm has presented in this paper. I have taken this to present you how this is going to work. So data, so load data processed, and after that it will check whether there is an electric vehicle available for charging or not. If it is not, fine. If it is yes, find the user's expected time of departure from final state of charge. So charging state, and when that user want that vehicle to be want to use his or her vehicle, that time input has to be there. Then your algorithm will find out that predicted power. If that predicted power is high, then definitely it will go for fast charging. If the predicted power is not high, is it normal? Then go for conventional charging. If it is low, then you use discharging to support the grid. Okay, so power needed for your vehicle is low, then you go for vehicle to grid charging. So this is how, just mere representation, this is how you are going to take a decision. Based on that, your EV will be fast charged or normal charge, or whether you are going to participate in vehicle to grid scenario or not. Now you can see here, if this algorithm is not there, simply you are putting every vehicle into DC fast charging, whether it is needed or not. So in this scenario, there are 3 options that is available. So if you have 3 vehicles, so in uncoordinated or when this algorithm is not in place, all the EVs will go into fast charging, because fast charging facility is available at that charging station. And unnecessarily, the fast charging, let's say if it is predicted power is low, your vehicle has not demanded high power for charging, even though you are charging at very fast rate. That is not recommended. Also, if charging is very low, then also it is not recommended. But we are not thinking anything, just we are putting into DC fast charging. That is not recommended. This is much more useful compared to previous one, because that this saves your time, this saves your battery, this saves the grid, and this saves the money as well. Okay, so this is a typical example. You can think of your own and think of a scenario and get the data set, and accordingly you can create an algorithm, and accordingly you can route the EVs to a particular charging station. So now you can see here how it is helping. You see here normal load curve. This black one is normal load curve with respect to time. So this is time, and this is load in megawatt. And the red one is uncoordinated conventional EV charging. So you can see there is a peak during this period, 6 at 6. There is a peak. And then you have managed EV charging. When EV charging you managed, you see green color. So power consumption from the grid is almost remain constant. You can see almost some variations, definitely it will be there. So it is almost constant. And there are, you see blue color. Here you are doing DC fast charging that you are doing. Here conventional charging that you are doing. And here vehicle to grid, because there was more power demand was there at this time. So instead of consuming power from the grid, why not to give power to the grid, so that this curve, curve can be made more flat. So this is how we can make that power consumption distribution. We can see throughout the day the distribution of power can be made flat. On the voltage fluctuation point of view, you can see here. So maximum voltage fluctuation, you can see here. The green one is the managed EV charging. I'm sorry. So managed EV charging, So here red one is the uncoordinated conventional EV charging. So there is a voltage fluctuation. So there is a voltage fluctuation. So variation, voltage variation. Here fluctuation is minimum. The green one fluctuation is minimum. And this is the normal maximum voltage fluctuation. When EV comes into picture, the fluctuation is more. So by doing a managed charging and coordinated charging, you can save the grid from power point of view and also from the voltage fluctuation point of view. But there is some limitation. Definitely you have definitely the system is working, but there is a problem with the solution. What is the problem? Main problem, when I went through different this machine learning based solution, I observed that the problem is the availability of data. Even if the data is available, that data is not sufficient to train the model to form an accurate model. That's the most difficult point in training that algorithm. So every time an algorithm run, accuracy may fluctuate and cannot be predicted with high precision. That's definitely, but that we have to bear with. Multiple times to validate, ensure high accuracy with small standard deviation. You have to ensure it. You have to ensure. That is why I was telling you. So for one parameter, if you are doing with some machine learning algorithm, you try to have it with other and see whether this error is less or not, whether you are getting more accurate result or not. That you can check and you can standardize. Okay, this I am going to use. The accuracy of the data set to train the model is model effectively. So accuracy of the data set should be there. Definitely, it is the machine is learning from a data set, and you are thinking. So let's say you are taking care of some equipment, and that equipment is behaving something, and you understand it will behave like this. Okay, you on a lift every day using the lift, and the lift is working smooth. So you will understand that okay, lift is fine and it is safe. And one day immediately you will feel that there is a free fall on the lift. It happens. That's very common. Okay. So if free fall happens, then you will understand, okay, there is a flaw and that data was not there in my mind. Okay. So if your data set is not accurate, whatever model that you are going to predict is not correct. Data set should be large and comprehensive to train and test the model accuracy. So that these limitations are there. So if data set is sufficient, accurate data is there, with the timestamp, you can definitely use and train your model. So conclusion is, so EV charge scheduling you can use machine learning as an optimization technique to minimize load variation, power losses, and voltage fluctuation. So transformer overload can be reduced, as we have seen that the load throughout the day we are making it flat, almost flat, and that when transformer is safe, the outage of the system is also, the reliability of system improves. Power loss reduces and voltage fluctuations are also improved. And there is a cost point of view. Okay, charging cost is reducing, so there is a customer satisfaction as well. So the major problem here is, as I already, so if I can summarize, the problem is if I say problem, I should not say problem. Now arena or the future is EV. Now when future is EV, and since renewables are coming up, not yet arrived or not yet the infrastructure has not built, so we are relying on conventional grid, and the EVs are charged from distribution grid. So there is a problem that when all the EVs are going to come and charge from the conventional grid, there is a problem that the voltage and power fluctuation, voltage fluctuation, the frequency fluctuation and variations will be there, which may lead to instability. So now you have the conventional grid, you have increased number of EVs, and you have increased number of charging stations. Now your job is to schedule the charging of these EVs from the charging station to save the grid. That algorithm you should work on using machine learning algorithm, and you can see whether it is that much effective or not. Some paper has reported some advantages are there. In reality, we need to put it into in practical case and need to see whether it is working or not. So that is what I was having to present. So references, and thank you. So if you have any questions, I can address.
If anyone having any question, please ask.
Sir, is I'm audible, sir?
Yes, yes.
Yes, you
Uh,
are audible.
So what about the, sir, thank you, sir. Thank you for the session. I'm Arul Kumar from SSN College of Engineering, Chennai. Sir, what about the data collection while working for reinforcement learning? What about the data collection? There's any existing data sets are there or?
Yes,
connection?
yes. There is a iHub in IIIT Hyderabad. They have data set and they made it public as well. I don't have exact URL of that, but you can search. It is available. They created
That
some
is-
data set
Okay, sir.
that is
Sir,
available. They announced.
IIIT Hyderabad, right, sir?
Yes, IIIT Hyderabad. They have took the initiative. I think they were. I don't remember exactly, but that data set. I don't remember exactly what kind of data set it was having. For road safety or for charging purpose, that I need to see. But you can check.
Okay, sir. So since you said that if you continually using DC fast charging, the battery it will drain soon, right? That was you mentioned in your session.
Uh, DC fast charging, if you do for your EV, any battery, if you do
Yes, sir.
DC or if you do fast charging of any battery, not DC, nothing. If
Okay,
you do
sir.
fast charging of any battery, then it's harmful for that battery.
Okay. So if that is the case, how can retain the battery life by is there any scope is there to work on that particular area by applying a ML and all, like to value the life of battery life or something?
Yes, yes. So battery state of health of the battery you can study. Okay, and based on, so if you observe the charging pattern of that battery, you can store that data, and your algorithm should take the decision whether at what charging rate it should charge at this state of health of the battery. Those kind of studies and those kind of implementation can be definitely done.
No, is any reference are there? The plenty of work is to work on that particular area. Since I belongs to computer science background, just I'm asking whether that area is feasible to work on, like
Yes,
predicting.
you can search actually. Yes,
Yes.
yes. That work is there, okay, but not that significant.
Okay,
But
sir.
what is last year, the initial days of last year, I did a study like that. What is the current, because this is very emerging topic. Okay, people are working like anything. So what is the current state of art is not known to me, but you can go through it.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Okay.
Thanks the organizing team for got the opportunity. Thank you.
Sir, I have a doubt. In this PPT, in the algorithm slide, if you can go to that particular slide, slide number 27. Sir, in this, the block which talks about use time of charge and total load to find mode, EVCS, this ML model. Sir, can you explain a bit about this part?
This is the main algorithm, machine learning algorithm that you have. You have the input, and then I told you whether grid is having that amount of power or not, and also amount of load currently that bus is having. Based
Okay.
on that, how much power that bus can cater. Based on that, you will take a decision, and also you will take a decision how much, because this user already gave some departure time or something. So now let's say a good amount of power that you need for charging that charging that EV. Now, if load is not having that amount of power, you cannot do that.
Yes. Yes, sir.
That bus is not having that amount of power. So those decisions that you are going to make there.
Okay. Okay. That's why after that, checking that particular power, we can move for fast charging, or we'll predict
Correct.
the power level. Okay, sir.
Yes, yes.
And sir, related to one topic that you discussed about I square R loss. So many a times these days we hear and we read in news about like fire taking place in electric vehicles. So is it the same concept that the heat is so much because of that I square R that fire took place, or because of state of charge of the battery? So what is the reason behind this? Uh, how can we analyze this part, sir?
Okay. Now see, you have very good two examples. One is battery that you use at home, inverter. Okay, that is
Okay.
one inverter that you have, and when you are going to buy from a shop, they will say that they will give a warranty of 4 to 5 years. Now you have EVs or eRikshaw. If you go and ask eRikshaw owner that what is the warranty of your battery, they will say 1 year. Okay, but also they will mention that they say 1 year, but that battery not goes to 1 year, but yes, somehow they manage 1 year. Why same kind of battery, lead acid battery in both the scenario, here it is less useful and there it is much useful. Home inverter, seldom you get a power cut, and for a small amount of time you use the battery. So its lifetime is good. When you have the battery that is used in EV, you frequently discharging the battery, very fast discharging the battery. Okay, now for a certain amount of time, you are heating the battery and then you are staying, the heating is going down. Now, what happens, it may not be I square R loss that much, but prolong such kind of uses, frequent charging and frequent discharging and discharging, the battery itself becomes weak, and battery quality becomes deteriorated. So you never know for what reason it has become damaged, and it might happen that there was some damage already has happened, and then when you started quick accelerating it because of high current, that I square R loss added to boosting it, and that battery got damaged. So there could be several reasons, because when you are discharging, when you are accelerating your e-bike, when you are accelerating, it is not huge amount of current that is coming, but current is coming at faster rate. Faster rate of change of current for a battery is also not good for a battery. So there could be reason, but may not be I square R loss may not be the only reason for those kind of scenarios.
Okay, sir. Thank you.
Anyone else?
I hope there is no query, sir. Very nice interaction, Indrajit sir.
Thank you, sir.
Yes, sir, and very good presentations. Lot of new thing we are able to know about your presentation. I hope the participants also get participants are also getting benefited and getting new idea based on the sustainable transportations and how the machine learning also been integrated with that EV ideas. Okay, thank you, sir, for your valuable time to us.
Thank you, sir. Thank you so much.
Thank you, sir.